One thing that's really cool about technology and mathematics, and this has always fascinated Mr. Adams, is that, well, we know from a physics perspective that notes have frequencies, and the frequencies are based on the oscillations or the waves, and we can tune those frequencies and we can calculate them mathematically. And so when they first came out with like electronic keyboards, what they did is they emitted a sine wave, and then they had knobs that allowed you to tune the frequencies. And now it's so sophisticated that you can buy a keyboard and it'll have a saxophone sound, but it sounds like a real saxophone. And really what they've done is they've modeled it mathematically. So they I don't know, I'm always impressed, and they have all these different, but it's all based on mathematical models, right? So they try to emulate what would it sound like if a live person played the saxophone. And those of you that are in band, you know that there's certain things that you could do with your instrument to produce a certain sound. And they just try to emulate all those things. So example number 5, what's nice about that is, so these things are sinusoidal, right? So sound is a wave, right? It's a mechanical wave where there's a compression of air that kind of moves through. It's not really a mechanical, I guess who you ask. But basically there's a compression of air that takes place, and it looks like a wave. And so if it continues in a certain way or frequency, then it'll produce a certain sound. So 1 hertz is really equal to 1 cycle per second. Okay, and so what this is saying is, it says find the sinusoidal regression equation. It's generally a sine curve for the data superimposed on the graph on a scatter plot. And then the second part says the frequency of a musical note or wave is measured in cycles per second or hertz, and the frequency is the reciprocal of the period. So if the period is equal to 2 pi over b, this is not in your textbook, but I want you to think about it. What is the frequency? What would the frequency be? It's the reciprocal, so it'd just be b over 2 pi, sort of, okay? Depending on what you're measuring, frequency and wavelength, sometimes they can have a scalar in between them, but they're generally reciprocals of one another. So what they want us to do, and so let me just throw up here what's in the textbook. What they have is a bunch of data, okay? And they've collected and created a scatter plot of the data, all right? And this is based on a tuning fork, all right? So there's pressure, and basically what happens is when sound is produced, there's pressure that compresses the air and then it releases, but it does so in such a way that it kind of creates a wave. So you have air pressure that kind of flows or resonates, and that causes the sound. And so if you take a tuning fork and you measure the pressure over time, you'll get data like this, okay? Now in that data, what you'll find is that the tuning fork, if we were to make a scatter plot of that information, there seems to be like a sine function of the data. So we could use this information to reproduce the sound of the tuning fork. In fact, an electronic tuner just collects this data and matches it up to what the note is supposed to be based on the frequency. Bless you. Bless you. So what we want to do is, there is a regression of this data. If we plug this in the calculator, we can make a sine model based on the sine function. In other words, my amplitude is 0.6, right? We'd have to factor out some stuff here, but there's a change in both the horizontal shift and in the actual period itself. And then we also have a vertical shift of 0.266. And so that's not necessarily what the question is asking us. What they're telling us is some information, and then we're going to try to figure out something. So part A says, find the sinusoidal regression equation. And so that is given to us. It's y equals 0.6 sine of 2488.6x minus 2.832 plus 0.266. Okay? And then, so that is just done by a calculator. So in other words, if I were to take all this data, plug it into my calculator, okay, which one is x and which one is y? Time is x and pressure is y. So if you were to enter that in your calculator, this will be L1 and this information will be L2. Does that make sense? And you would get a graph like this, and then you could just do a sine regression, right? And if you were to do that, it would produce this equation. Okay? So that's part A. So now part B is, it tells you that the period, if we were to solve this mathematically, we would have 2 pi, so this is the period, 2 pi over 2488.6. And really what they want us to know is to estimate the frequency. Well, how would we do that? Well, the frequency is just the reciprocal. So if I took 2488.6, okay, and then I put that over 2 pi, and I plug that in the calculator, it would be approximately 396 hertz. So what does that mean? That means that the tuning fork has about 396 cycles per second, right? And so lower frequencies, there's other ways to measure frequencies too. So what does this mean? Well, the interpretation of this information is that the tuning fork is vibrating at a frequency of 396. This is the G note above middle C. It is a few cycles per second different from the frequency of G we hear on a piano's tempered scale, which is actually 392. Okay? So now with the electronic tuners, so if you listen by ear and you think this is a perfect frequency, that's what they look for, and they'll tell you. Have any of you ever used the electronic tuner that'll tell you that it's sharp or that it's flat? Yeah. That's what it's really telling you is where the frequency is supposed to be and what you need to do to get there. And it's all done with sine waves. You're welcome.